Dear students, we have lecture number 3 of econometrics today. The topic for today's lecture is theory of correlation. The theory of correlation is one of the important theories of the econometrics, which shows the degree of relationship between two or more variables. So first we come to the definition of the correlation. It is defined as the degree of relationship between two or more variables. Two variables are said to be correlated if they tend to move simultaneously in some direction. If two variables simultaneously move in same direction or in opposite direction, we say that these variables are correlated. The correlation can be between two or more than two variables. If it is between two variables, we call this simple correlation. For example, the price and quantity supplied. If we find the degree of relationship between price and supply, then it is simple correlation. Similarly, the degree of correlation among more than two variables is known as multiple correlation. Similarly, we have the concept of the linear correlation. If you draw the points x and y on a scatter diagram, and we find that all the points lie near a straight line, it is called a linear correlation. Similarly, if the we can show it on the graph. If the points x and y are drawn on a graph, combination of x and y are drawn on a graph, and we see that all the points lie near a straight line or on the straight line, it is called linear correlation. If all the points on a scatter diagram seem to cluster near a curve, it is called nonlinear correlation. See in this diagram, look at this diagram. All the combinations of x and y, they lie near a curve. So it is a nonlinear correlation. Similarly, we have a positive correlation. Two variables are said to be positively correlated if they tend to move together in same direction. They increase or decrease in together. For example, price and supply. If the price increases, the quantity supplied by the producers or the sellers also increases. It is an example of positive correlation, simple and positive correlation. Similarly, the example of the sales and advertisement expenditure is also a positive correlation, because as soon as we increase the advertisement expenditure, it is expected that the sales will also increase. Negative correlation. If two variables move together in opposite direction, they are negatively correlated. For example, the price and quantity supplied. If the price increases, the demand falls, and if the price falls, demand decreases. If the price falls, demand increases. So both price and demand move in opposite direction. Other things remaining same, as according to the law of demand. So look at these diagrams. We can explain the types of correlation with the help of these diagrams. In this diagram, we see that all the points they lie near or on the curve, and the relationship is increasing one. If x increases, y also increasing. So it is linear because the points lie on a near curve, and it is a positive because with increase in the x, the y also increases. This diagram shows the positive relationship between if one increases, the other also increases. So it is if the x increase. Look at this. If this is x, this is y. If x increases to this, the y increases to this. So it is positive correlation, and as all the points lie near a curve, so it is non-linear. So the diagram shows positive non-linear correlation. Similarly, this diagram shows positive and this diagram shows negative and linear correlation. It is linear because the points lie near a line, and it is negative because the downward slope of the line shows negative correlation. It is another type of the correlation. It is non-linear because all the points lie and lie on the curve or near the curve, and it is negative because the curve is downward sloping, means if one variable increases, the other also increases. Similarly, dear students, this is an example of the zero correlation because we find all the points scattered on the diagram. The scatter diagram just shows an idea of correlation, and often we need the strength of correlation. Means this diagram show that just that these variables are x and y are correlated positively or negatively, but this does not quantify the relationship. For precise quantitative measurement of the degree of correlation between x and y, we use a parameter called correlation coefficient. So for quantitative measurement of degree of correlation between x and y, we use a parameter called correlation coefficient. Means the value of the correlation coefficient quantify the correlation between two variables x and y. The value of the correlation coefficient r lies between -1 and 1. We can use this formula: rxy is equal to summation small xy divided by under the root summation small x square under the root small y square. Here the x and y are in deviated form, so we can calculate the small x by the formula capital X minus x bar, while the small y can be calculated by capital Y minus y bar. The concept of the correlation coefficient was first given by Carl Pearson in 1896. The statistic is over 125 years old and is still going very strong. It is one of the most widely used statistics after the mean. The correlation coefficient denoted by R is the measure of strength of straight line or linear relationship between two variables. The correlation coefficient, by definition, assume any value in the interval between +1 and -1, including the end values of +1 and -1. Dear students, keep in mind these points which you see in this slide to make decisions on the basis of the correlation coefficient. The higher the value of the correlation coefficient, the stronger the type of relationship. So the following points are the accepted guidelines for interpreting the correlation coefficient. Dear students, if r square is equal to 0, it means no linear relationship or zero correlation, no correlation. Similarly, if r square is equal to +1, it means perfect positive linear correlation. As one variable increases, the value of other will also increase. If r square is equal to -1, it means perfect negative linear relationship. As one variable increases in its values, the other variable decreases in its values through an exact linear order. Similarly, if r square is equal to 0 is between 0 and 0.3, it means positive. It means a weak negative linear positive correlation. If r square lies between 0 and 0.3, it is a weak positive correlation, and if it is between 0 and -3, it is weak negative correlation. Similarly, the r square, if the r square is between 0.3 and 0.7, it will be moderate positive correlation, and if it is between -0.3 and -0.7, it is a moderate negative linear relation. Similarly, if the r square lies between 0.7 and 1, it means strong positive linear correlation, or if it is between -0.7 and -1, it is strong strong negative linear correlation. Students, we can explain the concept of this simple linear correlation with the help of an example taken from Corciani's theory of econometrics. In the first leftmost column, we have the number of observations. In second column, y. In the third column, the capital X. We have the formula r is equal to summation small xy divided by summation small x square under the root summation small y square under the root. So now we have to calculate the value of small x and small y first, then small x square, small y square, and then small x y. So in this table, first we calculate the small x, which is actually capital X minus x bar. So we first calculate the x bar and subtract each value of the x bar from capital X. So if we add all the observations of the capital X, we get summation x as 110. The number of observations are 10, so x bar is equal to summation x over n. So summation x is 110, n is 10, so 110 divided by 10, we get x bar 11. Now we subtract 11 from each observation of the capital X and get the column for small x. So 11 minus 2 minus 11 minus 9, 4 minus 11 minus 7, 6 minus 11 minus 5, 8 minus 11 minus 3, 10 minus 11 minus 1, 12 minus 11 1, 14 minus 11 plus 3, 16 minus 11 plus 5, and so on. Similarly, the small y is equal to capital Y is equal to capital Y minus y bar. Y bar is a summation y over n. So we add up all observations of y, then we will get the summation y. Summation y is the summation of the observations, all observations of y, which is 610. So summation y over n is y bar. Y bar is equal to summation y over n. So 610 divided by 10, 61 is the y bar. We subtract the value of the y bar, that is 61, from each observation of the capital Y. So if 10, we subtract 61 from 10, we get minus 51, the first observation of small y. 20 minus 61 minus 41, 50 minus 61 minus 11, 40 minus 61 minus 21, 50 minus 61 minus 11, 60 minus 61 minus 1, and so on. So this is the value of small y. Now according to the formula, we need small x square, small y square, and small xy. So first we square get the small x square by taking the square of all observations of the small x. So if we take the square of minus 9, we get 81 in the column of xi square. Similarly, the square of minus 7 is 49, the square of 5 is 25, the square of minus 3 is 9, because we know that if we take the square of minus, it becomes plus. Minus 1 square 1, and so on. So if you take the square of each observation in the column of small x, we get its corresponding value in the column of small x square. After taking the square of all observations. If we add all the observations of small x square, we get summation small x square, which is 330 in this case. Similarly, for getting the small y square, we square all the observations of small y. If we take the square of the minus 51, we get 2601. If we take the square of minus 41, we get 1681. The square of minus 11 is 121. The square of minus 21 is 441. The square of minus 11 is 121. The square of minus 1 is 1, and so on. Similarly, if we add all the observation of small y, we get summation y square 10490. The next factor which we need is small xy. So if we multiply the small x with the small y, each observation in the small x column with each observation of the with the corresponding observation of the small y, we get the corresponding value in the xy column. So minus 9 into minus 51, 459, because 9 ones are 9, minus minus becomes plus, 9 ones are 9, 9 fives are 45. Similarly, minus 7 multiplied by minus 41 is 287. Minus 5 into minus 11, minus minus plus, and 11 fives are 55. Minus 3 into minus 21, it is 63. Minus 11 into minus 1 into minus 11 plus 11 plus 1 into minus 1 minus 1, 3 into 19, 57, 5 into 29, 145, 7 into 29, 203, 9 into 59, 531. So if we add all the values in this column, we get 1810 is summation xy. So we got all our relevant factors. Summation x square is 330, summation y square 10490, summation xy is 1810, and now we put these in the formula. The formula is correlation coefficient formula is R is equal to summation xy divided by summation small x square summation y square. So the value of the small xy is 1810. So we put it here. So 1810 divided by summation x square, that is 330 under the root, and then 10490 under the root. By solving it, we get 0.975, which is the required value of the correlation coefficient. Rank correlation coefficient. Dear students, the calculation which we made was for the general formula of the linear relationship between two variables. That formula was based on the assumption that all the observations are quantifiable, and all the observations are quantitative, and they have accurate measurement. But sometimes it happens that all the observations may not be measurable, or they not may have the quantitative value. They may be qualitative or may be binary variables like profession, education, preference, or particular brand. Profession means employed, unemployed, educated, illiterate. So here a response is binary one, where for one we put 1 and 0. So you may have preference for a brand among different brands. In such cases, it is difficult to calculate the correlation coefficient through general formula of correlation, and in such cases we use a rank correlation coefficient. We rank the observations according to the specific sequence, size, importance, etc., using numbers 1, 2, 3, 4 up to n. In other words, we allot ranks to the observations. The following formula is used to measure the correlation in such cases. R is equal to 1 minus 6 summation di square divided by n into n square minus 1, where d is capital D is the difference between two ranks, while n is the number of observations. We have an example here. There are students A to J, and in the first row, the second row shows The ranking based on classwork, while the third row shows ranking based on exam marks, and you are supposed to find out the correlation between ranking of the classwork and the exam marks. So first we find the D. We know that D is the difference between two ranks, so we subtract the values of the exam marks from the values of the classwork. So 2 minus 1, 2 minus 1, 1, 5 minus 6, minus 1, 6 minus 4, 2, 1 minus 2, minus 1, 4 minus 3, 1, 10 minus 7, 3, 7 minus 8, minus 1, 9 minus 10, minus 1, 3 minus 5, minus 2, 8 minus 9, minus 1. And then we, in order to get the D square, we square all the observations of the row D. So the square of 1 is 1, minus 1 square 1, square of 2 4, square of minus 1 1, the square of 1 1, square of 3 9, and so on. If we add all the observations of the D square row, we get summation Di square is 24. And if we put the values in this formula, 1 minus 6 summation Di square is 24. Number of observations is n, so 10 into n square, 10 square minus 1, we get the R as 0.855. Similarly, we have another example, the brands of cigarettes. The market researcher asked two smokers to express their preference for 12 different brands of cigarettes, and their replies are as shown in the following table. We have 12 different brands of the cigarettes, and there are two smokers, Z and W, and they have been asked to show their preference. The observations are given in the table. These are the preferences of the smoker Z, and these are the preferences of the smoker W. We subtract in the same way the observations in front of the W from the Z, like 9 minus 7 2, 10 minus 8 2, 4 minus 3 1, 1 minus 1 0, 8 minus 10 minus 2, 11 minus 12 minus 2, 8 minus 10 minus 2, 11 minus 12 minus 1, 3 minus 2 0 minus 1, and so on. And then we square them and take the square as we get the summation D square as 50, and when we put it in the formula, we get 0.8207. So dear students, this was an introduction to the theory of correlation. This is your homework. You can solve these two examples to find the correlation coefficient. If you want to know the details, all these details have been taken from the Cortiani's book, Theory of Econometrics. So for the details, you can give a reading to this book. I suggest you to give reading to this book. Thank you very much.